Hey everyone, and welcome. Today we're diving into the amazing chemical power couple that, believe it or not, shapes just about everything around us: acids and bases. I'm talking about the food we eat, the products we clean with, even the very blood pumping through our veins. These two opposites are in a constant, vital dance. So let's get started with a simple question.
So think about this for a second. What could a sour, zesty lemon possibly have in common with a bar of slippery soap? I know, it sounds a bit like a riddle, right? But the answer actually shows us that they're just two sides of the very same chemical coin. And that question leads us perfectly into their most obvious characteristics. The ones we can actually see, taste, and feel. So how do we physically experience acids and bases in our everyday lives?
On one hand, you've got acids. The word acid actually comes from the Latin word for sour, so that sharp taste of a lemon or vinegar is a dead giveaway. Then you've got bases, which are the opposite. They tend to taste bitter. And that weirdly slippery feel of soap or bleach, that's not just some coating. It's literally the base reacting with the oils on your skin and turning them into a tiny, tiny amount of actual soap. Pretty wild, huh?
Now, in a lab, we obviously don't go around tasting things. So the classic go-to way to tell these two apart is the litmus test. It's a super simple color code. Acids turn blue litmus paper red, and bases do the exact opposite, turning red litmus paper blue. It's just a really simple visual way to confirm their opposing natures.
Okay, so we know how they taste, feel, and how they test. But what's actually happening on a molecular level to make them so different? Well, it all comes down to these tiny charged particles called ions, and the whole show gets started with one key process. And that process is called ionization. So just picture a substance dissolving in water. Instead of just floating around in one piece, it actually breaks apart, releasing these electrically charged little things called ions. This one simple act is what gives acids and bases all of their incredible power.
And here's the crucial part. When an acid ionizes in water, it releases hydrogen ions, that's H+. But when a base ionizes, it releases hydroxide ions, or OH-. These two ions, H+ and OH-, are the key players. They are the fundamental chemical opposites that define whether something is an acid or a base.
Now, like with any big scientific idea, our understanding of this didn't just appear overnight. It actually evolved over time. It got broader and way more sophisticated, leading to three major theories that kind of build on top of each other. It all started back in 1883 with a guy named Arrhenius. Then jump forward 40 years to 1923, and we get a massive expansion on the idea with the Bronsted-Lowry theory. And get this, in that exact same year, Gilbert Lewis comes along and gives us the most comprehensive definition of them all.
And this table just lays it all out perfectly. So Arrhenius gave us a great starting point, but he only focused on what happens in water. Acids make H+ ions, bases make OH- ions. Simple. But it turned out that was a little too narrow. That's where Bronsted-Lowry stepped in. They zoomed out a bit and said, look, an acid is anything that donates a proton, which is just another name for that hydrogen ion, and a base is anything that accepts one. This is pretty much the most popular definition we use today. And finally, Lewis zoomed in even further, right down to the electron level. He defined acids as electron pair acceptors and bases as electron pair donors. Think of it like a chemical handshake. The Lewis base offers up a pair of electrons, and the Lewis acid accepts them. Each theory just gives us a bigger, more complete picture than the last.
Right, so we know what they are and how we think about them, but how do we measure just how acidic or basic something is? How strong is it? Well, that's where one of the most famous tools in all of chemistry comes into play: the pH scale.
The pH scale runs from 0 all the way up to 14. But here's the most important thing to remember. It's a logarithmic scale. That means that a pH of 2 isn't just a little bit stronger than a pH of 3, it is 10 times more acidic. And a pH of 1 is 100 times more acidic than a 3. Every single number you go down is a 10-fold leap in power.
And this really puts things into perspective. The incredibly powerful acid in your stomach that digests your food, that sits at around a pH of 2. The ammonia you might use for cleaning is way up on the other end, at a pH of about 11. And right there, smack in the middle, we have the point of perfect balance.
And that perfect balance point is the number 7. Pure, distilled water is the very definition of neutral. It's not an acid, it's not a base, it's sitting right in the middle of the scale. It's kind of like the chemical Switzerland.
So now we get to the really cool part. What happens when these chemical opposites actually meet? They don't just hang out. They react in this incredible process called neutralization.
And it follows this beautifully simple formula. You take an acid, you react it with a base, and what do you get?
Salt and water. That H+ ion from the acid and the OH- ion from the base get together to form H2O. Yep, just plain old water. They basically cancel each other out, creating something totally neutral.
You've actually experienced this if you've ever had heartburn. That burning feeling, that's from too much stomach acid. So when you take an antacid, what you're really doing is swallowing a mild base, and that base gets to work neutralizing all that excess acid and bringing you relief. It's a perfect real-world example of this chemistry in action. And this balance isn't just about comfort. It's absolutely essential for life. I mean, look at this tiny range. Your blood has to be kept between a pH of 7.35 and 7.45. If it strays even a tiny bit outside of that incredibly narrow window, your body's systems just start to shut down. That is how critical pH balance is to our survival.
Now, because these substances are so powerful, especially when they're concentrated, working with them requires an absolute, no-excuses commitment to safety. And there is one golden rule that every single chemist knows by heart.
The rule is AA, always add acid. That means you slowly and carefully pour the concentrated acid into a larger amount of water. You never, ever do it the other way around. If you add water to acid, the reaction can be violently exothermic. It releases a massive amount of heat so fast that it can cause the whole thing to boil and splash dangerous concentrated acid everywhere. So remember, AA.
So when you bring it all together, you realize these aren't just some abstract concepts from a textbook. They are the fundamental forces that govern the world, both inside our bodies and out, defining everything from the taste of our food to the very possibility of our existence.
And that leaves us with one last little thing to think about. We know that milk is actually a little bit acidic. Its pH is just under 7. So why does it sometimes feel so soothing on an acidic, upset stomach? It's a great question that just goes to show how nuanced this whole chemical dance can be. Thanks for tuning in.